Today I'm going to walk you through our latest concept, which is called the mole. So a mole is a unit in chemistry that we use to measure the amount of something. It's also called Avogadro's number after the guy who basically discovered it. And this is how much a mole represents, 6.02 times 10 to the 23rd particles. In other words, if I was to have 1 mole of eggs, I would have 6.02 times 10 to the 23rd eggs. If I had 1 mole of pennies, then I would have 6.02 times 10 to the 23rd pennies. So a mole is an amount. I couldn't say how much would a mole weigh, because a mole of eggs would weigh a different amount than a mole of pennies. Now, obviously, this is a really big number. If you had a mole of eggs, it would take up a huge amount of space. But remember, when we're talking about atoms and molecules, particles, in chemistry, they're extremely small. You can't see one carbon atom. But you could actually see a mole of carbon atoms. So a mole, the reason we use such a big number is because atoms and molecules are so small. Okay, so now that you know what a mole is, we can learn how to do a conversion between moles and particles. So in this case it says how many water molecules are there in 12 moles of water. So we already know from our previous slide that 1 mole of water, 1 mole of anything, but water in this case, would be equal to 6.02 times 10 to the 23rd molecules of water. So we're going to use dimensional analysis, which we learned earlier in the year. And I realize that you may not want to use this, that it may seem that it's complicating something that's very simple. However, you'll see that when we get later in this chapter, and especially when we get to the next chapter, using dimensional analysis to organize your conversions is going to make your life a lot easier. So remember, dimensional analysis was a way of setting up conversions. In other words, if 1 mole of water is equal to 6.02 times 10 to the 23rd molecules, that means you could set it up as a fraction, that 1 mole would be equal to 6.02 times 10 to the 23rd molecules, or 6.02 times 10 to the 23rd molecules would be the same as 1 mole. So we can set this up as a fraction because basically this is saying 1 over 1. Alright, now here's the important part. We start always with what we're given. So in this case we were given 2 moles of water. Now, in order to convert, we need to choose which of these 2 fractions will cancel moles, because that's what we're starting with, and get us to particles. So since in our original number, moles is basically our numerator, 2 moles of water is the same as 2 moles of water over 1, we're going to put moles on the bottom. We're going to use this second one. So if we put 6.02 times 10 to the 23rd molecules of water on top is the same as 1 mole of water on the bottom. Notice that moles will cancel, and now we multiply the 2 times the 6.02 times 10 to the 23rd, and we get 1.2 times 10 to the 24th molecules of water. And technically, if we're going to use significant digits for this, our significant digits are going to be based on solely on our original measurement, which was 2 moles. So in reality, this answer would be 1 times 10 to the 24th water molecules. So this technically would be our answer. So here are some more practice problems. This one says, how many molecules are there in 8 moles of carbon dioxide? Okay, so again, we're looking for molecules, and we know that 1 mole of anything, in this case carbon dioxide, is going to be equal to 6.02 times 10 to the 23rd molecules of carbon dioxide. So again, we're going to start with the one thing we've been given, which is 8 moles. And again, we're going to set up this fraction so that we cancel, in this case, moles. So our 1 mole is going to go on the bottom. 6.02 times 10 to the 23rd, that's how many of them there are in 1 mole. Moles will cancel. This is carbon dioxides. And our answer, again, I'm just going to round to 1 digit since my original number was 1 digit. So my answer is going to be 5 times 10 to the 24th molecules of carbon dioxide. Alright, let's look at our next one. How many moles do we have if we have 7.3 times 10 to the 50th particles? Alright, so what were we given to start? 7.3 times 10 to the 50th particles. They don't say what it's particles of. It really doesn't make a difference. And this time we want particles to cancel. So we're going to set it up this way. 1 mole of particles is equal to 6.02 times 10 to the 23rd particles. And notice now particles will cancel. Now, because this is on the bottom, we're going to divide. So we're going to put in our calculator 7.3 times 10 to the 50th. Then we're going to divide it by 6.02 times 10 to the 23rd. Always, if something's on the top, you're going to multiply, and if it's on the bottom, you're going to divide. And this time we get 1.2 times 10 to the 27th, and in this case moles. That's what we were converting to. Alright, last one. How many moles are there if we have 5.7 times 10 to the 18th formula units of sodium chloride? Now don't forget what a formula unit is. Since sodium chloride's ionic, formula unit technically means kind of the same thing as molecule, but for an ionic compound, because ionic compounds don't consist of molecules. So don't let formula unit throw you off. So we're going to start with what we were given, which is 5.7 times 10 to the 18th formula units of sodium chloride, and they're asking for moles, so we're going to put 1 mole on the top, and our 6.02 times 10 to the 23rd on the bottom, and again that means we're going to end up dividing, and we get 9.5 times 10 to the negative 6 moles. That's not a negative number, remember. What that means is we have 1, 2, 3, 4, 5, 9, 5 moles. It's just a really small number. So that would be our answer. Okay, so now we're going to look at a different aspect of moles. So remember how we figured out how much an atom weighed? We used atomic mass. And if you go to the periodic table, I have a really tiny one here, but it was this number underneath it. So in the case of oxygen, let me see if I can make this a little bigger. Alright, so if I make this bigger, we see that, for example, the atomic mass of oxygen is 15.999, or approximately 16 AMU. AMU was atomic mass units, and that was the unit that we used to measure a single atom. So that means that 1 atom of oxygen has a mass of 16 AMU. How about 1 mass of carbon? Well, we go over here to carbon, and one atom of carbon has a mass of 12 AMU. So atomic mass units are how we would measure the mass of a single atom of any element on the periodic table. And for the purposes of this, we're rounding a little bit. So for example, for aluminum, it says 26.98. So we're just going to round that up and say that a single atom of aluminum would weigh approximately 27 AMU. Okay, so this is a different aspect of the mole. in the lab, okay, we're not going to use AMU. I'm not going to send you to the balance to weigh out 1 atom of oxygen because it would be way too small. So here's the beauty of the mole. A mole of any element, meaning 6.02 times 10 to the 23rd atoms of that element, will be equal to its mass in grams. In other words, if we go to the periodic table, and again, and this is going to be called molar mass, by the way. So here's our oxygen again. So we said that a single atom of oxygen weighed 16 AMU. So what we're saying is if I had an entire mole of oxygen, if I had 6.02 times 10 to the 23rd oxygens, how much would they weigh? They would weigh 16 grams. So we just change AMU to grams. So how much would 1 atom of copper weigh? Approximately 63.5 AMU. But how much would an entire mole of copper, 6.02 times 10 to the 23rd coppers weigh? 63.5 grams. So if we change AMU to grams, what we're saying is that's how much a mole of that atom would weigh. So neon, 1 neon atom weighs 20 AMU. A mole of neon, if I had 6.02 times 10 to the 23rd neons, those would weigh 20 grams. Now notice, we could measure that in the lab. If I sent you to the balance, I could say, measure out for me 1 mole of carbon. And you'd say, well, how much does a mole of carbon weigh? Oh, 6.02 times 10 to the 23rd atoms of carbon will weigh 12 grams. So if you went to the balance and weighed out 12 grams of carbon in that sample, you would have approximately 6.02 times 10 to the 23rd atoms of carbon. Okay, so we can do this for an entire compound. In other words, let's say I wanted to know how much carbon dioxide weighed. Okay, a single carbon dioxide. I would go to the periodic table, and if you remember from the previous slide, 1 carbon weighed 12 AMU. And oxygen weighs 16 AMUs, but notice in carbon dioxide there are 2 oxygens, so we'll multiply this times 2. So the oxygens in carbon dioxide would weigh 32 AMU. If we add this together, the 32 AMU and the 12, 32 and 12, 2 and 2 is 4, 3 and 1 is 4. So that means that the formula mass, the mass of a single molecule of carbon dioxide, would be 44 AMU. That also means that the molar mass, the mass of 6.02 times 10 to the 23rd carbon dioxides, would be equal to 44 grams. Again, this is an amount we could measure in a lab. AMU is not. So you could measure out exactly 1 mole of carbon dioxide. It would weigh 44 grams. On this slide, we have the same thing showing water. Water, the atomic mass of hydrogen is 1. And there's 2 of them in a water molecule. And then oxygen is 16. And there's 1 of those in a water molecule. If we add this up, we get that a single molecule of water would weigh 18 AMU. But a mole of water, an entire 6.02 times 10 to the 23rd atoms of water, or molecules of water, would weigh 18 grams. And this would be called the molar mass. 18 grams of water would be 6.02 times 10 to the 23rd molecules. And here it is one more time. This time we're doing the molar mass of glucose. In other words, this is glucose, sugar. And if I wanted to figure out how much an entire mole of glucose would weigh, if I had 6.02 times 10 to the 23rd glucose molecules, how much would they weigh? Well, carbon weighs 12 on the periodic table, and there's 6 of those in glucose. Hydrogen weighs 1, and there's 12 of those in glucose. And oxygen weighs 16, and there's 6 of those in glucose. Multiply and add, and we get that an entire mole, 6.02 times 10 to the 23rd molecules of glucose would weigh 180 grams. How much would one glucose molecule weigh? 180 AMU. All right, a couple more problems. So our next one asks what the molar mass of methane is. So we can go to our periodic table and put it over here. And we can look up the individual parts of methane, carbon, and 4 hydrogens. So carbon weighs 12, so that's 12, plus hydrogen, if we go back over here, weighs 1. Here's our hydrogen. And there's 4 of those. So if we come back over here, we have our 12 of those plus 4 times 1, 4 of these. So a mole of methane would weigh 16 grams. Now for nitric acid, hydrogen weighs 1. Nitrogen is cut off here, but nitrogen weighs, there it is, 14. And oxygen weighs 16, and there's 3 of them in the formula. So 6 times 3 is 18, so that's 48. If we add those 3 numbers together, we get 63 grams. And that means that a mole of nitric acid weighs 63 grams. And 1 molecule of nitric acid would weigh 63 AMU. The last one, vinegar, works the same way. We can actually combine the 2 hydrogens here. There's a total of 4 hydrogens in this. So carbon weighs 12, and there's 2 of those, plus hydrogen weighs 1, and there's 3 of those, or I'm sorry, 4 of those. And oxygen weighs 16, and there's 2 of those, so that's going to be 24 plus 4 plus 32. So if we add all that together, we get 60 grams. So 1 molecule of vinegar would weigh 60 AMU, and a mole of vinegar would weigh 60 grams. Okay, so this means that we can convert between moles and mass. And you have to be really careful with this. Notice the question, what they're asking you. So here they're saying, how many moles of sodium chloride would there be in an 11.2 gram sample? So they're giving you how much it weighs, and they're asking you how many moles it will be. Now we just learned that 1 mole of anything, NaCl in this case, would weigh 58.5 grams. They're not asking you how many atoms there are. You're not using 6.02 times 10 to the 23rd here. Okay? If they were asking you how many sodium chlorides would there be in a mole of it, then yes, you would use this to figure out how many there are. But this time, they're saying you went to the balance, you weighed out this much. They want to know how many moles that is. Well, if we know how much 1 mole of it weighs from our periodic table, we can figure out how many moles we have in this sample. So again, we start with the piece of information we're given, 11.2 grams of sodium chloride. So we know that 1 mole of sodium chloride weighs 58.5 grams. And this is off the periodic table. I took a shortcut. I didn't show you how to add them up. So grams of sodium chloride will cancel in this case. Because this is on the bottom, we're going to divide. Alright, so here's another problem. Again, make sure you pay attention to what you're being asked for. So they want to know how much 2.5 moles of sodium chloride will weigh. So we're starting with 2.50 moles of sodium chloride. If they wanted to know how many formula units that was, we would be using our 6.02 times 10 to the 23rd. But they don't want to know how many. They want to know how much is that going to weigh. Alright, so going to the periodic table, I just gave you the mass of this. It's 58.5 grams. That was on the previous slide. So if 1 mole weighs 58.5 grams, That means 1 mole weighs 58.5 grams for sodium chloride. Why did I put moles on the bottom this time? Because moles is what we want to cancel. That means this time we're going to multiply. Okay, and when we do that, when we multiply that out, we get, I'm going to round to 3 significant digits again, we get 146 grams of sodium chloride. So in other words, if I was to weigh out 146 grams of it, I would have 2.5 moles of it. How many formula units would I have? I would have to use my 6.02 to figure out how many. All right, here's another one. How many moles are in a 20-gram sample of silver chloride? So we're starting with 20 grams of silver chloride. Now, in order to answer this question, we know that 1 mole of silver chloride is going to weigh whatever its mass is on the periodic table. Alright, so if we look here, silver weighs 107.8, give or take, 107.87. We can round it to 108 if we wanted to, I guess. So 108 for the silver. And chlorine, I always put 35.5 because it's sort of right in the middle. So 35.5. Now we need to add those up, 108 plus 35.5. And we're going to get 143.5 grams. So that's how much a single or a mole of silver chloride weighs. Alright, so plugging that in, 1 mole weighed 143.5 grams. Since we want to cancel grams, I put grams on the bottom. That means we're going to divide. Alright, and we get 0.14 moles of sodium or silver chloride. Technically, again, if we wanted to pay attention to significant digits, this 0 doesn't count. So in reality, we would have to say this was 0.1 moles of silver chloride. I'm not going to get that picky with you guys, but as long as you're setting them up properly, that's really what I'm concerned about. Okay, and this brings us to our final aspect of moles. We know that if we have a mole of something, we can figure out how many we have. And we can also figure out how much it weighs. It turns out with gases, there's a special conversion that we can do. We can figure out the volume or how much space a mole of a particular gas will take up. Now this only applies at what we call STP. And STP actually stands for standard temperature and pressure, which happens to be, that should be 0 degrees Celsius and 1 atmosphere. So the rule is that a mole of any gas, doesn't matter what the gas is, will always take up the same amount of space at 0 Celsius and 1 atmosphere, and that amount of space is 22.4 liters. So in other words, if I had a box that held exactly 22.4 liters of gas, and I cooled that box to exactly 0 degrees Celsius and had the pressure inside at exactly 1 atm, whatever gas is in that box would be a mole of gas. So if I put oxygen in that box under those conditions, that would be 1 mole of oxygen gas. If I put nitrogen gas in that box under those conditions, I would have exactly 1 mole of nitrogen gas. So this is a different aspect of moles. And this is called molar volume. Again, it only applies to gases, and it only applies to gases under these conditions, which is called STP. So in other words, here's our first question. What would be the volume of 6 moles of oxygen? Alright, so we start with 6 moles of oxygen, which happens to be O2, by the way. Remember, because of Hofbrinkel from our previous chapter, but it really doesn't matter for the question that you're being asked because it could be 6 moles of any gas. It could be 6 moles of oxygen, nitrogen, just 6 moles of air, carbon dioxide. It doesn't matter because we're being asked for the volume, and the volume is a constant under standard temperature and pressure. The volume of any gas, 1 mole, in this case of oxygen, how much space is it going to take up? Exactly 22.4 liters of space. Now, if they asked how much it weighed, we would not use this conversion. We would look up how much it weighs on the periodic table. If they asked how much do we have, how many molecules of oxygen do we have, then we would use our 6.02 times 10 to the 23rd. But they're asking how much space it's going to take up. And this is our conversion for how much space it's going to take up. Sort of like if we were talking about eggs. If I said you had a mole of eggs and I said how many would that be, you know you would use 6.02 times 10 to the 23rd to figure out how many eggs you would have in 10 moles of eggs. But if I said you had 10 moles of eggs, how much would they weigh? Then you would actually have to look up how much one egg weighs and then go from there. In this case, we're asking how much space it takes up. So if you somehow vaporized your eggs to a gas and wanted to know how much a mole of eggs, how much space that would take up, then you would use this conversion. So if you multiply this out, you would get that 6 moles of oxygen would actually occupy 134 liters of space. Now, I should comment again, for significant digits, technically this can only have one. So I guess your real answer here, if you're going to get technical, would be 100 liters of space. But again, what we are looking up is how much space would 6 moles of oxygen occupy, and 134 liters, or technically 100 liters, would be our answer. Okay, here's 2 more practice problems. So this time they're telling you have 100 liters of carbon dioxide, and they want to know how many moles you have. All right, so they're telling you how much space it takes up. They want to know how many moles it is. So we're given 100 liters of CO2 times, and in this case, we want to cancel liters, so 1 mole of CO2 takes up how much space? 22.4 liters of space. So we're going to divide, and we get 4.46 moles. Since we only had one significant digit, I guess we'd have to round that technically to 4 moles of carbon dioxide. But the important thing is that you divide to cancel liters. Last one, we have 20 moles of helium. They want to know how much space that's going to take up. So 1 mole of helium would take up 22.4 liters of space. Therefore, 20 moles of helium would take up 448 liters of space, or since we only have one significant digit, I guess we'd have to round that to 400 liters of space. All right, so this chart I looked up on, found it, it's kind of cute because it has moles on it. This kind of gives us a roadmap so that we could get from any one unit to any other unit. And notice that moles are at the center of this. So here's our moles in the middle. If I have a mole of something and I want to know how much it's going to weigh, this is where I would go to the periodic table and use the molar mass. That 1 mole would be equal to, let's say it was oxygen. So let's say we have a mole of oxygen. How much is it going to weigh? Oh, well, we're going to use 1 mole of oxygen is equal to, and we'd go to the periodic table, and it turns out that a mole of oxygen would weigh 32 grams. On the other hand, if we had a mole of oxygen and we wanted to know how many molecules of oxygen we had, in this case, a mole of oxygen would be 6.02 times 10 to the 23rd molecules of oxygen. So we would have 6.02 times 10 to the 23rd oxygens, or oxygen molecules. And in theory, we could take this a step further. If we said, okay, so this is how many particles of oxygen we have. What if I wanted to know how many actual atoms that would be? Well, every oxygen, O2, actually consists of 2 atoms. So in theory, we could go another step and we could say, oh, so if I wanted to know how many total atoms of oxygen I had, I could take that number and I could multiply it by 2. In other words, I have 2, I guess I could write it out like this. I have 2 atoms of oxygen for every 1 O2 molecule. So I would be multiplying by 2. Finally, if I had a mole of oxygen gas at standard temperature and pressure, and I want to know how much space it's going to take up, I go this direction to volume, and I know it would take up 22.4 liters of space. So moles, if I have a mole of oxygen, I can actually know 3 different things about it. I can know how much it's going to weigh, I can know how many molecules it's going to be, and assuming we're at standard temperature and pressure, I can know how much space it's going to take up. Now, this flowchart is almost like your Bible for this chapter. You've got to memorize this. You've got to know when you're given one piece of information and asked for another, you've got to figure out where you need to go. Where are you starting and where do you need to go, and figure out which conversions to use. The hardest part of this test is that I will give you moles, let's just say, and I will ask you for how much it's going to weigh. And people will use the 6.02 times 10 to the 23rd. You can't use that. I'm not asking you how many. I'm asking you how much it's going to weigh. So this is extremely important. So to wrap it up, I put 3 sample problems here. These are multi-step problems. So take a look at our first one. How many grams are there in 6.02 times 10 to the 24th molecules, it should say atoms actually, atoms of silver metal? So we start with what we're given. So we have 6.02 times 10 to the 24th atoms of silver. Now, what they want to know, what we've got to eventually get to, is how much that silver is going to weigh. But in order to get there, if we go back to our previous slide, what we're going to have to do is we can find out how many moles of silver that is, and then from moles, we can figure out how much it's going to weigh. So our first step is that we're going to get to moles, because moles, we can relate moles to anything. So we know that 1 mole of silver is going to be 6.02 times 10 to the 23rd atoms of silver. And notice that now atoms will cancel and we'll get moles. Now, if you stop here, your answer will be in moles. But what we can do is we can keep going. If you have trouble with this, if you don't understand how to keep going, go ahead and get an answer here in moles, and then do your next step separately. But really what you want to do is get to where you can put this entire thing together. All right, so we've gotten to moles. We also can relate moles to grams. So right now we have moles of silver, and I know that 1 mole of silver weighs 108 grams. Now, how do I know that? I'm not magic. I went back 2 slides and peeked at the periodic table. So you go to the periodic table, figure out how much a mole of silver weighs, and now what we can do is we can work our way straight across here. In other words, what we're going to do is we're going to start with our 6.02 times 10 to the 24th. This is on the bottom, so we're going to divide by 6.02 times 10 to the 23rd. Then we're going to keep going, and we're going to multiply by 108. So we're going to divide, then we're going to multiply, and we're going to get our final answer. Okay, so I worked this out, and if I stop here, just for the record, I would get 10 moles. In other words, if I just do our first step, 6.02 times 10 to the 24th, divided by 6.02 times 10 to the 23rd, I get 10 moles of silver. But I don't need to stop there. I just kind of wanted to show you that we could stop there. Our next step, we'd multiply by 108 grams, and we get this number right here, 1,080 grams of silver. So if I had 6.02 times 10 to the 24th atoms of silver, how much would they weigh? They'd weigh 1,080 grams. And I got that by going to moles first, and then from moles to grams. So let's look at our second problem. So our second problem says, how many oxygen molecules are there in 20 liters of oxygen gas? All right, so we're going to start with the one piece of information we were given, 20 liters of oxygen gas. First step, we got to get to moles. So in this case, we're going from liters to moles, and they want to know molecules. All right, we don't even need the periodic table for this, by the way, because the liter conversion and the molecule conversion are both constants. So it doesn't even matter what gas we're starting with here. So 20 liters of oxygen, our conversion to get from liters to moles is that 1 mole of oxygen, or any gas, is 22.4 liters. If we were to stop here, our answer would be in moles. But since they want molecules, we can go one step further. Right now we have moles on the top, so we're going to put moles on the bottom, and 1 mole of oxygen gas is 6.02 times 10 to the 23rd molecules of oxygen gas. And now we're going to work our way across. We're going to first divide by 22.4, then we're going to multiply by 6.02 times 10 to the 23rd. Okay, and I get 5.375 times 10 to the 23rd molecules. Technically, we'd go back to the beginning, look at our first number, which only has one significant digit. So in reality, our really, truly correct answer would be 5 times 10 to the 23rd oxygen molecules. That's how many molecules we'd have. How did we figure that out? We knew how much space it took up. So from there, we figured out how many moles we had. And once we knew how many moles we had, we could figure out how many particles that would be. And our last question here asks, how much will the oxygen weigh? So we already know how many particles we have, but we can actually we can start from anywhere. I'm going to go ahead and go back and start with our original 20 liters. So we had 20 liters of oxygen. Again, we're still going to moles. Our first step's exactly the same. So 1 mole of oxygen would take up 22.4 liters of space. Liters will cancel, but this time they want to know how much it weighs. And so if we go to the periodic table, we're going to find that oxygen weighs 16, and there's 2 of them in O2, so that's 32 grams. So 1 mole of oxygen, this way moles will cancel, weighs 32 grams. So to solve it, we will then take this number. First we'll divide, and then we're going to multiply. And I get 28.57 ... In theory, one significant digit, so we would actually round that to 30 grams of oxygen. And so that would be our final answer. Okay, so to summarize what we've learned, or what you should have learned, is that moles are sort of a central unit that can be used for multiple conversions in chemistry. First of all, we know, for anything, we know that a mole is 6.02 times 10 to the 23rd of that thing. So if I want to know how many do I have, if I have some number of moles, I can figure out how many by multiplying, or I can go the other way and divide from moles to particles. If I want to know how much a mole of some particular thing weighs, or vice versa, I have a mass and I want to know how many moles I have, so this is going to be our mass, then I'm going to go to the periodic table and I'm going to use molar mass. For example, if it was oxygen, then I would know that 1 mole of O2 would weigh 32 grams, or 1 mole of carbon would weigh 12 grams, etc. And finally, only in very, very specific cases, if we are at standard temperature and pressure and we're talking about gases, I can also figure out how much a mole of gas will take up. Or if I have gas in a box at those conditions, I can figure out how many moles I have if I know the volume of the gas. And our constant here is 22.4 liters. Okay, you need to be able to do what I just did. You need to be able to draw this and know which direction to go. I should be able to give you any one thing on this table and a periodic table, and you should be able to go from particles to mass, from mass to liters, from any one of those things to moles. That's what you've got to be able to do to be successful in this chapter. And our next chapter, which has an evil name, it's called stoichiometry. If you don't understand this chapter is going to really wreck you. So you have got to understand this chart, or not only are you going to have problems in the rest of this chapter, but the next chapter you're going to be completely lost. So I hope this helps. do all the worksheets. I've given you worksheets and answer keys with them. Work as many problems as you can. Check them with the answer key and make sure you're getting them right. And if you're not, come and see me so that I can help you.